Welcome to another episode of the Understanding Crypto series by Thomas Plunkett. Today, we're going to take a look at disassembling Ethereum Virtual Machine bytecode. This is part of our exploration of the Ethereum Virtual Machine. This video and these slides are under a Creative Commons license. So let's talk about disassembling EVM bytecode. This is a great way to understand how high-level solidity acts in the Ethereum Virtual Machine. There are several disassemblers you can use to do this. Porosity is a popular open source decompiler. Ethersplay is an EVM plugin for Binary Ninja, which is another disassembler. And IDA EVM is an EVM plugin for IDA, which is yet another disassembler. And there's others. This is just a few of them. So we're going to take a look at the Ethersplay plugin for Binary Ninja. So, and we're going to continue to use the example of the faucet solidity smart contract that we've talked about several times in these lectures. So we're going to get the runtime bytecode for faucet.solidity, and then we're going to feed it into Binary Ninja, assuming you're using the Ethersplay plugin, to see what the EVM instructions actually look like. So here's a quick look at what, just a reminder as to what our faucet.solidity is doing. It's, basically a hello world contract. It's got the smart contract faucet. It's got a withdrawal function that does a transfer of ether to do a withdrawal, assuming that the amount you're withdrawing is actually in the account. And then you've got your fallback function that receives payments. Okay, so here is a look at our output from the disassembler. We can see here we got a dispatcher, we got a central block, we got a withdrawal function, and we got the fallback function. So when you send a transaction to an ABI compatible smart contract, which you can assume all contracts are, the transaction first interacts with the smart contract's dispatcher, this thing up here. The dispatcher reads in the data field of the transaction and then sends the relevant part to the appropriate function. So this is going to check to see, hey, are you calling withdrawal function? Are you calling fallback? What's actually going on? So we see an example of the dispatcher here at the beginning of our disassembled faucet solidity runtime bytecode. Now after and if we dive in, we can see these instructions here. You've got your pushes, you got a store, you got another push, you got a call data size, a less than, a push, and a jump. So we can look at those. We saw previously this push 60, push 40 M store, which is just, putting 60 and 40 on the stack and then storing 60 at the 40 address. Now what's happening with this push, this call data size, the less than, the push, and the jump? These various steps in the dispatcher. So what they're doing is push one is followed by 0x4 is pushing our hexadecimal number 4 onto the stack. Call data size gets the size in bytes of the data sent with the transaction and pushes that number onto the stack. So now our stack has a length of the call data as well as hexadecimal 4. Lesser than pops the two top values of the stack, and if the transaction data field is less than 4 bytes, it will push 1 onto it. Otherwise, it pushes 0. So if we assume that the data field was less than 4 bytes, now our stack has a number 1 on it. The push 1 hexadecimal number 0x3f is just then going to put, hex value of 3f onto the stack. And after this instruction, the stack looks like this. We've got hexadecimal number 0x3f and 1. Remember 0x3f is going to be 3 times 16 plus the numeric value of f, which is 15. So that's going to be, that's actually the equivalent of 53 right there. The next instruction is jump on one, which stands for jump if. It works like a jump if label comma condition. So jump to the label, that's where we're going, if the condition is true. In this case, it's kind of like an if else if you think about it. In this case, label is 0x3f, which is where our fallback function lives in our smart contract. So we'll jump to that location if this condition argument is true. Now the condition argument is 1, which is a result of the lesson instruction earlier. And so 1 is always going to be true. So then we'll jump there. Now, if it had been 0, we would not jump there. So basically what this entire sequence is doing is jump to the fallback function if the transaction data is less than 4 bytes. So if we go back to our little dispatcher here, if the transaction data is less than 4 bytes, we go to fallback. Otherwise, we're going to go through here and then through there into the withdrawal function. So now at the fallback function, we kept that fallback function pretty much empty. So all we have in here is a stop instruction because it's an empty function. Now, assuming we receive some call data that was greater than 4 bytes in length, the jump instruction would not jump to the fallback function. Instead, the code execution would proceed to the instructions here in the middle with this push, call data load, push 29, swap, and so on. So here we can see those called out, push 1, the number 0, call data load, push 29, 0x1, 1 followed by a bunch of zeros, swap 1, divide, push 4, and do push 4 followed by a number, then equals, and then push 1, and then jump. So let's walk through what each of these instructions are doing. So push 1 to 0 is going to push 0 on the stack, which is now otherwise empty again. That's a hexadecimal version of 0. Call data load, accept as an argument index with the call data sent to the smart contract and reads 32 bytes from that index. So now we see 32 bytes of call data starting at byte 0. Since 0 was the index passed to it from the push 1 0 command, call data load reads 32 bytes starting at byte 0 and then pushes it to the top of the stack. And the original 0 goes away at that point. After the next command is push 29, 0x100. So we put 29 bytes long, 0x100. One followed by a bunch of zeros. And so now we have these 2 long numbers on our stack. A 29 byte long number that begins with 1 and a 32 bytes of the call data starting at byte 0. Swap 1 then switches the top element of the stack with the ith element after it. In this case, it's switching the 2 numbers on the stack. And so our new stack is just switched. Then the next instruction is div, which is basically integer division. So in this case, we have our 32 bytes of call data starting at byte 0, and then we have y equals 0, x, 1 followed by a bunch of zeros up to 29 bytes. So the hexadecimal number that begins with 1 is pretty darn long as a 1 followed by all zeros. Dividing the 32 bytes of call data by this value essentially is going to drop off everything except for the 4 bytes of the top 4 bytes of the call data load. And those 4 bytes, the first 4 bytes in the call identifier, are our function identifier. And so that's how the Ethereum Virtual Machine identifies the function identifier field by just doing that division. Now we've got this push 4 hexadecimal number, and we can ignore that as the stack's going to remain the same. The dupe one is just going to duplicate the first item in the stack, which is a function identifier. So now we have the two function identifiers in the stack. And the next instruction, push 4, followed by this strange number, hexadecimal number 2E1A7D4D, is going to push this pre-calculated function identifier, the withdrawal function. So this is the identifier of the withdrawal function onto the stack. So now we have two function identifiers set in data, and we get the one that was pushed on the stack to identify the withdrawal function. Now we're going to use the equal operator to do a comparison of the top two items in the stack. And so this is where the dispatcher is doing its main job. It's comparing the function identifier that represents the withdrawal function with what was computed based on the input that was passed in. If they're identical, then we know that you called withdraw. Otherwise, we'll push a 0 on the stack. So if they're equal, we'll push 1 on the stack, and that'll be used to jump to the withdrawal function. Otherwise, we'll be pushing 0 on the stack, and we will not be jumping to withdrawal. So now the stack has a 1, and it's got the function identifier. Now we push 1, followed by the memory address 41, which is the address of the withdrawal function. And then the jump I instruction comes next, and it will allow us to jump to the location withdrawal function, and then the withdrawal function's code will be executed.